So hi everyone, we're just now going to review conditional probability. We'll bring back the rabbits for a moment. Then we're going to take a look at Bayes' theorem as it applies to medical testing. So we're going to take a look at the accuracy of medical tests like the COVID lateral flow test and so on, and see how population size and other ideas can make a difference to what you will discover. So let's make a start straight away. Let me just pick up the next slide. We're going to take a look at our rabbit review, first of all, just to remind ourselves of what we've learned about conditional probability. I'm going to start off with 72 rabbits, different kinds of rabbits, and we're going to split those into male and female. And the numbers in the brackets there represent the proportion of males and females, or if you like, the probability that if you randomly picked one of the 72 rabbits, you would get a male 41.7% of the time and a female 58.3% of the time. We're now going to split the male and females into those that might eat carrots and those that might not eat carrots. And once again, we have 72 in total, but this time the males and females, as well as having their percentages at the bottom of the screen down here, right, we've now split them by rows into those who would eat carrots and those that wouldn't eat carrots. So 0.459 that wouldn't eat carrots and 0.541 that would eat carrots. So we've got all of our numbers and we've got our appropriate probabilities for each one there. The 72 at the bottom is the total probability. So let's just review our terminology, bring this slide back up here. And in this one, we've got those males there, okay? And the probability of you being a non-carrot eating male, in this case, is going to be, well, what's the probability that you're a male? 0.417. The probability that you don't eat carrots, 0.181. And you're going to divide the 0.181 by the 0.417, and you find the, given that you're a male, what's the probability that you are not a carrot eating rabbit? Okay, so here we go. In this case, given that you choose a male rabbit, what is the probability that the chosen rabbit does eat carrots? So this is the opposite of the one I've just explained. 0.236 up here divided by 0.417 equals 0.567, which is equivalent to 17 out of 30. Fairly obvious there, 17 carrot eaters and 30 males altogether. So now we can move on. If we turn that into mathematical symbols, the probability that you are carrot eater, given that you are male, is the intersection of male and carrot eating, which is here, male and carrot eating in the orange, divided by the probability that you are male. So that's the mathematical statement. So what we've done is we've conditioned the probability by using the subset of rabbits that are male to calculate the required probability. On condition that the rabbit is male, does it eat carrots? For now, we're not interested in the female rabbit's carrot eating habits. So back to the top again, 72 rabbits. We're going to write this in a slightly different way. This is in the form of a tree diagram. So we split it 30 male, 42 female. The males, 17 of them eat carrots, 13 don't. Same for the females, 20 carrot eating females and 22 non-carrot eating female rabbits. Okay. So this is our original thing here, the carrot eating males. Where does that come from? It's quite simply the 17 over 17 plus 20, 17 over 37.459. And that is a result of, excuse me, it's going a bit nuts here. So here we're just going to change the colours and try and keep a track of where the colours are going. Rabbits, male, carrot eating male rabbits, and non-carrot eating male rabbits. Okay, the numbers are appearing there, 30 out of 72, 42 out of 72, 17 out of 30, 13 out of 30, 22 out of 42, 20 out of 42, and then our probability that you are female and not, given that you don't eat carrots, well, there it is, the probability of female and not carrot eating, which is down here in the green, down in the right hand side there. And then the total probability that you are not a carrot eater is going to be the probability of coming from rabbits to males to non-carrot eating, and female to non-carrot eating. You add those two together on the bottom line. You do the calculation and you arrive at the fact that the probability that you're female, given that you don't eat carrots, is 0.604, which might seem a little bit odd, bearing in mind that there are a lot more non-carrot eating female rabbits, 20 out of 42 compared to 13 out of 30. Okay, so you actually get a higher proportion, and that can sometimes be a result which confuses people about conditional probability. It's not just the actual probabilities that count, but it's also the numbers that are involved in the calculation. And in this case, there are a greater number of female rabbits than male rabbits, and that pushes the percentages up towards the female end of the scale. So despite the fact that male rabbits tend to prefer carrots more than females, if we choose a non-carrot eating rabbit by random, it will more than likely be female, which seems counterintuitive when you look at the numbers the first time round. And it's this counterintuitive result which is at the heart of what we call Bayes' theorem, where we have to take into account what's happening in the background as well as the probabilities that we're looking at in the foreground. So when it comes to probability testing, we use the same idea for medical testing. A tested population, right, the whole of the country during the COVID, split into people who are infected and tested and the people who are uninfected and tested. These in turn split into they are infected and the test they took gave a positive result. In other words, a true positive. They were infected and the test said they were infected. We balance that with an infected person who gives a negative result, what we call a false negative, in that it should have detected the fact they were infected, but it didn't. And that happens with medical tests for a number of different reasons, which we don't want to go into here. So the uninfected test gives a positive result. That's a false positive. They are uninfected, but the test indicates that they are positive. And the final category, they are negative and the test shows that they are negative. So that's a true negative result. In medical testing, we use some language, particular language. Prevalence is how many people are there in the population with a particular disease. On the other side, 1 minus the prevalence, those who are not infected with the disease, the complement of the prevalence. The sensitivity is a measure of how good the test is, how sensitive it is to testing. And 1 minus sensitivity on the other side. Specificity, which is a measure of whether it will only be able to detect the disease that you want. Okay, it's specific for one disease. And 1 minus specificity on the other side. Then this monstrous looking thing on the bottom, but you should be able to follow because I've kept the colors all lined up. What is the probability that you are positive, given that you tested positive? So the given is that you've tested positive, this yellow box on the left hand side. Now, what is the probability that you really are positive, given that that has happened? So we take our probability that you are positive and you intersect that with the tested positive. And then what is the probability that you tested positive? Now this bit on the bottom comprises two results. It's the two yellow boxes here. Test gives positive result, test gives positive result. The second one is where you're actually not infected at all. So if we follow the green colors in the boxes, we end up with that statement that you're going to get prevalence times sensitivity divided by prevalence times sensitivity, which is one of the ways you can be found, plus the other two sides, the 1 minus prevalence times the 1 minus specificity. And that then gives you what's called the positive predictive value. Okay, it's able to detect positive when it should. Okay, so to illustrate what might happen then, right, some little definitions coming on here. So we can look at those. Now, let's put some numbers in. prevalence 0.05. Now what that means is that we are able to measure the actual number of people in the population that are positive, and that would usually be by a much more detailed test, such as a PCR test, which is much more reliable, much more accurate than a lateral flow test. So we imagine that 5% of the population is infected, 95% is not infected. Our sensitivity, in other words, our test is 0.9, which means that 0.9 of the time it will give a positive test when you are positive. Obviously, it's 1 minus sensitivity on the other side. Specificity is 0.8. It will detect that you are negative when you are negative. And the other bit there, 1 minus specificity, 0.2. Now, in this case, the positive, given you are positive, given that you've tested positive, same thing as we've just done. Now we've just put the numbers in from our chart here, and we arrive at this statement here, that in a situation where you've got a test which is 90% accurate and is also able to detect the correct disease 80% of the time, those seem like big numbers, it turns out that you are positive that you test positive. Given that you test positive, you are positive, it's 0.192. I'm not quite sure if I said that correctly, so I'll say it again. The probability with these figures that you see on the chart that you are positive, given that you tested positive, is only 19.2%, which many people find to be, wow, that's not very good, is it? And this is a truth, yes. Usually, though, these numbers here, the sensitivity and the prevalence numbers are higher, and this comes to a slightly higher number. We can show on a spreadsheet what those numbers might actually be. But the first thing to get, and this is where we're heading in towards Bayes' theorem, is that really the accuracy of a test in terms of its positive predictive value, it shows you positive when you are positive, is very much dependent on the choice of the figures or the sensitivity of the tests. And very often in probability, a lot of the work is in deciding what the sizes of these numbers should be, the specificity size, the sensitivity size, and so on. So just to finish off there, what's the likelihood that you are positive given that you test negative? So that's quite small. It's less than 1% there, which is quite a relief. So if you do test negative, you might actually be positive, and the negative test hasn't found that that is actually true. And that's the end of the video. You can watch it as many times as you like to make yourself clear, but that's the beginning of what we call Bayes' theorem. So until the next video, thank you very much. Goodbye.